So by considerations such as this and knowing what the residuals in the Tully-Fisher relation are, so roughly the scatter in the Tully-Fisher relation is something like 0.46 magnitudes. We can actually apply a very strong constraint on what the mean ellipticity of the potential is in the midplane of disks of typical Bose galaxies. This is work that was done in 92 by Frankson and Zhou. So actually what their conclusion was that given this amount of scatter, typical disk cannot have an elongation in the potential, not in the density. The density is typically usually more elongated than the potential is. The typical elongation of the potential would be of order 0.1. And in fact, it's highly unlikely that all the scatter that we observe is due strictly to just ellipticity of disks. So in fact, probably the typical ellipticity of disks and their potentials is considerably smaller than that. It might even be completely consistent with completely due to observational errors. So this sets already at the outset a very strong constraint on how triaxial dark matter halos are, at least in the vicinity of where disks are. Another classical method by which people have tried to measure the shape of the potential or the shape of the dark matter halo is through Sagittarius streams. So the Sagittarius dwarf has fallen into the Milky Way, and if the halo potential is not perfectly spherical, the streams that come off the Sagittarius dwarf are going to precess, they're going to precess. And then you would try to measure the velocities, or you would measure the velocities, and you would try fitting the velocities as a function of position based upon modeling the triaxiality of the halo. And so there is there is one reason why we want to try to really constrain the shape of the dark matter halo. One of the most promising ways of constraining the shape of the Milky Way is something that's called 1,000 kilometers per second. Now in that process, because that's happening right at the center of the Milky Way, the star that comes out has essentially no angular momentum. So that's great, because if the halo of the Milky Way is spherical, you would expect a perfectly radial orbit. Whereas if the halo is triaxial like this, you might expect something different. That's the velocity. There's some acceleration perpendicular to the velocity, and at the end of the day, when you observe the star, you would find that it has a very large velocity, but that velocity is not pointing back to the center of the Milky Way. And in fact, if we use, in future, if we start using satellites like Gaia, for example, to give us a very good handle on positions and velocities, full three-dimensional velocities of stars like these, we can start comparing the radial velocity and the deviation from the radial velocity that the deviation of the velocity I observe from purely radial, and that will tell us something about the shape of the halo. So here is an example of a prediction from Gnadin et al. This is if there's only the disk potential, it will give you a deviation in degrees that reach a peak of about 0.4 degrees at about 10 kiloparsecs, whereas a triaxial halo would give you a much larger deviation, well, a larger deviation at a much larger distance. In fact, there's some claim that some of them have not come out directly from the center, but in future we expect that we'll probably get a lot more of these objects to allow us to constrain the shape. There's simulations of galaxy formation from Balin et al., 2005, and what he finds is the polar ring galaxies. Polar ring galaxies were traditionally thought to be one other way, this is a somewhat older idea, goes back by looking at warps. And what I'm going to spend a fair bit of my time on is showing you the line in the main plane of the dark matter halo, shown by that line. And they start out with a simulation. It's got roughly the mass of the Milky Way, radius of the halo, and then there's gas that comes in along streams and enters into the halo. Well, what we did then was we went to look at the torques technical, the dark matter halo is speaking of that. What we find is like this. So the very first talk we heard at this workshop, at this conference, was already within 2 kiloparsecs. And it gets worse and worse as you move upwards. And of course, can evolve at the limit of stability, and this is actually what we find when we run simulations that are, again, what's invoked in the first talk we heard. The idea here is that the sun will give us a signature in muons, which people are starting to build instruments and big experiments to detect. And because of this enhancement due to the rotation of the dark matter halo, you actually get an enhancement of the expected signal that you expect to see from these things. So this is the halo where spherical, we would expect some signature, some flux of muons that is a few times 10 to the 3. Whereas if you have this disk of dark matter rotating rapidly, the signature, the flux, actually jumps up by roughly an order of magnitude, by a factor of 10. So this will be a very nice result. This is really happening in nature. We should be able to actually get an enhanced detection rate of annihilation products coming from the center of the sun. So things like Super K, Amanda, and the ice cube experiment. Okay, I'm going to switch gears a little bit and tell you a little bit now about understanding the shape evolution of dark matter halos. And before jumping into that, I want to tell you a little bit about the orbits of stars or dark matter particles in triaxial systems. These are not this, these are halos, these are the halos. So there are the classic box orbits. These are the orbits that pass arbitrarily close to the center. Then there are various loop orbits. There is a short axis loop orbit. Those are stars or particles that loop around the short axis of the halo. And then there are the inner and the outer long axis loop orbits. And those are particles that loop around the long axis of the halo. You will notice that there is no intermediate axis loop. And the reason for that is because those are violently unstable, so you never get those. And you need to be able to build a triaxial halo from the combination of this, and that. And so what we've done is we've been very interested in looking at these orbits in our simulations. So I started off this talk by telling you that most of the time when we look at dark matter halos, what we think we see are not triaxial halos, but things that look more spherical. There's been two ideas, two very different ideas. One is, can we artificially evaporate? Now, this is all purely artificial, of course, but it tells us simulations, well, many more, but I'm presenting 3 simulations. One with a disk grown in it. System, you grow the baryonic component in the center, you get rounder, you get significantly rounder in both cases. Now, I mean, I showed you this sort of in a relatively spherical system. In a spherical system, all orbits should be irregular. They should all be studied where box orbits. After we grow the disk inside it, what we find is one axis divided by the frequency along another axis. And you see that there are some resonant orbits over there. These correspond to banana orbits. These are in triaxial halos. It's been shown that if you have a barred galaxy in a triaxial experiment, I remind you again what so that's the orbits that are circulating around the minor axis. You have box orbits, banana orbits.